So hi, I'm going to talk about type systems, and by the end of my talk, you'll learn why they're useful and how they can help you write better code. It is a bit early, so I have a cheap speaker's party trick. To keep you from falling asleep, please give me a round of applause whenever I drink water. Shall we give that a try? Y'all are awesome, thank you. So I'm really excited about this talk, and I spent way too many hours down the rabbit hole researching type theory, but I distilled it down, and I have some pro tips to share with you to help you write better programs. It's a very deep topic, and I've learned a lot about type systems as well as functional programming, and I hope you will too, because functional programming is notoriously unfriendly to beginners, so I hope this talk will change your mind. Before we begin, small warning, there is going to be code and math in this talk, but if I do have to use jargon, I will explain it. So can I get a quick show of hands, how many of you have shipped a bug into production? I know I have. We're all human, programming is hard, and it's really easy to add bugs into software, especially in the Wild West that is JavaScript. And when bugs inevitably happen, I feel pretty terrible about it, and you experience a real crisis of confidence, sometimes especially if you can't figure it out. But when you do, all is good in the world, and your confidence is restored. So I've been programming for a while now, and I've seen my fair share of JavaScript errors. And here we have everyone's favorite, undefined is not a function. Now, I don't know about you, but these type errors just aren't my type. I just want to swipe left, turn everything off, drink a hot chocolate whenever I see one. Oops. But on the other hand, I've grown to love working with types on top of JavaScript. I primarily use TypeScript for personal projects as well as at work, and I'm in love. Flow is also an attractive option. It has a number of differences compared to TypeScript, but you can use it as well to statically type your code. But in this talk, I will be using TypeScript examples. And I also wanted to briefly talk about GraphQL if I don't run out of time, which is an interesting way to deliver a type system over the network. So my name is Lauren, and I'm an engineering manager at Netflix, and I ship bugs into production, yay. Confusingly, I have many internet handles. On Twitter, I'm SugarPirate with an underscore, and on GitHub, I'm Potato, but with an E. Clearly, I'm not very good at the internet. So what is a type system other than something that yells at you a lot? There are many different definitions, but my explanation is that a type system is a way to add constraints to code. A type system is there to help you enforce the logic that is consistent within those constraints. But why? Why are constraints useful in your code? So here's my bold claim. Constraints are good because they limit the number of bugs in your program, and let me explain with an example. Here we have a simple function. It takes one argument and divides it by 2. How many ways can this function fail? Well, I came out with some possible inputs into this function. We have our usual suspects like null, undefined, numbers, strings, and so on. And now I want to enumerate over all of those inputs, and after running this code, we should see an array of test results. So let's run this in our console and see what happens. Unfortunately for us, null and undefined do not have any methods on them. Now, wouldn't it be nice if the compiler could tell us? Like, I don't want to have to wait to run this code manually in the browser to find these bugs, or have to write a million unit tests because I'm really lazy. And this is only a simple function, like dividing by 2. So in JavaScript, your first instinct might be to start adding checks for null or undefined, or even to define undefined as a function. But you end up having very defensive code, and you're checking argument types in your functions, which are, again, only checked at runtime. So you're shipping more code to the browser, which is fine, I guess. But I know it's really frustrating not being able to catch these simple bugs before you ship them into production. Drink water. I'm really good at drinking water. So anyway, if we fix the errors and run our program again, we'll see that most of these inputs throw type errors or result in some kind of nonsensical value, like not a number. So let me ask you again, how many ways can that function fail? think about every single one of those inputs that you could pass into this function. There is an infinite number of permutations. There is an infinite number of permutations of garbage you could pass to this function. You could give it an array of 11 ones, or an array of 1,000,000 eights, 100,000 character string. They would all cause problems. Now using TypeScript, let's add the simplest type annotation to drastically constrain the function down to only accepting one set of types. And now x can only be a number, and the compiler will yell at me if I pass in anything else. Now if you try running this function with every single number possible in JavaScript, in theory, none of them should cause an error, at least at compile time, and assuming you have typed your program correctly. But in most cases, this function is what we call total. So my bold claim for today is that types and constraints will reduce the bugs in your programs. So today we're going to look at a brief introduction to TypeScript, some background into type systems and how it can help you write better programs, and also explore what it means to have a type system over the network. So we briefly saw what types in TypeScript look like. Let's learn some of the simple basics to establish the foundation for the next topic. I'm not going to go through everything here, so don't worry too much about syntax. Focus on the ideas, and you can always look up the syntax later. So first, let's look at variables, something that you probably use all the time, I hope. You specify the type after the variable name, and these are actually both equivalent since TypeScript can infer the type, even if it's not explicitly declared. For lists or arrays, you have to tell TypeScript what kind of array it is. For example, number square brackets means an array of numbers. You can also define your own types. Here I've made my own type called server stacks. This is a union of string literals, meaning that anything that has this type can only be one of these exact strings. You can also define interfaces which describe the shape of a user object, much like in Reason. And you can also describe functions with interfaces. So this is a function that takes an argument of type user. It knows that isAdmin is a Boolean type on that interface that we defined earlier. So obviously, I would not be able to assign it to 1, which is a number. And this is all caught for you at compile time. And if you use VS Code, you also get a nice red squiggly line plus an error message. So those are just the basic examples. And again, don't worry about the syntax. Remember the ideas. Everything in JavaScript has a type. It could be a primitive type, like a number or a string. It could be a function. It could be a user-defined type or interface. And these all describe the kinds of things that make up your application. Now I want to talk about how you can make your types reusable, just like you make your code reusable. MakeArray is a simple function that takes a value x and puts it into an array. But what we have here only covers numbers, strings, and booleans. What about objects? What about my own types? What about symbols, class instances, and so on? How can we type this function so it can accept any type without me having to define every single one of these functions because I'm lazy, but still have type safety? The answer is to make it reusable as a generic function. So notice that the function logic itself hasn't changed, only the type signature has. So let's walk through this. The first thing you should notice is the single letter T in pointy brackets. This is a type variable, much like a regular variable, only it's for types. And this tells TypeScript that this function is generic. It can work over more than one type. If you want to get fancy, like what Ken was saying just now, this is also called parametric polymorphism. You can go tell your coworkers that. But most people say generic. In our function arguments, we say that x is of type T. And this captures the type of whatever was passed into this function and says, let T be the type of this argument x. So this could be a string, this could be a number, it could be a user, whatever you pass into this. And you can use this type variable later in your signature. And finally, you specify the return type of the function, which in this case returns an array filled with items of type T. So now when you're using this function, TypeScript knows how to guide you. You pass in a number, it knows that it will return an array of numbers. And if you pass in a string, it will return an array of strings. So this is a very simple example, but also very powerful because it helps you reuse your types and not have to repeat yourselves. Here's another example to drive things home. This map function is generic and takes two type arguments, a and b, and we're going to use these type variables later. Map takes two arguments, first a function and then a list of items. The first argument is a function. It takes a single argument of type a, and returns a single value of type B. The second argument is an array of items that are type A, and the return value is an array of items that are type B. Just by reading this type signature, can anyone guess what this function does? It's pretty obvious, but this function is exactly like array.map. And with this type signature, TypeScript knows how to type accordingly based on what you pass into it. And more importantly, you will know what is returned without having to actually evaluate the function. And you can now think about how your functions compose based purely on the inputs and the outputs of that function. So we looked at some high-level concepts, and again, don't worry about the exact syntax. Focus on the ideas. Recall earlier we talked about how many ways that program could fail. Having types mean that your functions and classes can specify constraints about what can be passed into them. So there's a lot functional programming can teach us, and if you're interested in learning more, check out these videos that I linked to at the bottom of this slide. All right, now we're getting to the exciting part. So type systems are grounded in mathematics, and so is functional programming. Interestingly, type systems can also be applied to object-oriented languages, and the concepts behind this are pretty interesting, and I think it can really help us understand why type systems help us write better code. So let's start with a very quick high-level overview of what functional programming is. Functional programming is the practical implementation of mathematical theories. We have proof theory, which is all about constructive proofs and mathematical proofs. Constructive logic and mathematical proofs. We have category theory, which is about algebra and how functions compose. So if you've ever heard of things like monoids or functors or monads, these are examples of categories within category theory. And then we have type theory, which is about programs and the idea that propositions are types. So Curry, Howard, and Lambeck are logicians and mathematicians who independently found that these three mathematical theories were describing the same idea in different ways. So this correspondence is the relationship between these three theories, the proof theory, category theory, and type theory. If this sounds arcane to you, don't worry. I'll try my best to explain, as I promised earlier. So the key takeaway I want you to have is this. Propositions are types. So here my type signature states that given two numbers, x and y, a number exists. And the idea that programs are proofs of those propositions. Because you don't just get to say that things are true, right? You have to prove it. You have to show your work. And x plus y is a proof that a number exists. We're going to revisit this again later to see why that idea is useful. But let's take a quick look at functions, not in the programming sense, but from a mathematical perspective. So this is a function as described by mathematics. In plain English, this function maps an object of type A to an object of type B. Pure functions, if you know what they are mappings. For a given input, you get an output in return, and you always get the same output. And note that object here does not refer to a JavaScript object, but an ordinary object, unrelated to programming. So remember what we said earlier. Types are propositions. They assert that something is true, something exists. For example, this function will return a number. And our programs are proofs, the implementation, the actual function body. A number exists because here I have produced the number 1. And so type checking is really proof checking. And if you work backwards from that, what this means is that if you write good types, you can let the type system suggest the implementation for you, basically type-driven development. And in theory, you could declare all of your types and all of your function type signatures without writing any actual code. And if it compiles, like Ken did on the airplane, your program should just work. Then it's just a matter of filling in the details, proving that those propositions are true. So let's start with a concrete example in TypeScript. This function takes a list of items and returns the first one. Once you've written the type signature, the implementation sometimes seems very obvious. For example, if you try returning the list itself, you get a TypeScript compile error because we're not returning the right type. We're returning an array instead of a single item. So let's return the first item in the list because there's actually very little else you can do here. And you might notice that we could actually return any index of this list, not just the first one. So this here is an example of a limitation of TypeScript's type system. in that you cannot check that you're actually returning the first element of this array. Other more functional languages like Idris have more advanced type systems, and this may be possible with dependent types, but my point is that TypeScript is not a silver bullet, but really a pragmatic way to balance productivity and type safety. And looking at our map function again, if you try it out iteratively, we return the items on their own, and we'll also see compile errors since items is obviously still a list of objects of type A, and it does not prove that our proposition or type signature is true. Now, if you call that the callback function on a single item in the list of items, you're going to get a little bit closer, except that you're not returning a list of Bs, you're only returning a single B. So logically, the only thing you can do here is to take the callback function and run it on every item in the list. And this seems obvious if you know how array.map works. And what about React? The nice thing is its elegant mental model, right? Your view is a function of state. And stateless components are functions. They take props and they give you a React node. So trying it out with the number 1 obviously doesn't work because Lauren, 1 is a number, not a React node. And if you make it a function that returns 1, it obviously doesn't compile either. So logically, the only thing you can do is to return a JSX element. Thinking in type signatures and pure functions makes it way easier to compose functions and for you to start thinking about how you can create higher order components as well in React. So let's revisit the implications of the Curry-Howard-Lambek correspondence, the idea that these 3 mathematical theories are related, and learn how it can help you write better functions. Here we have a graph of the function f of x is equals to x squared. What I'm trying to call out here is that pure functions in JavaScript are similar, if not the same, as the functions you learned in high school math. But some terminology before we go further. Pure functions, as I explained earlier, map inputs to outputs. And when I talk about the domain of a function, that refers to the set of all possible inputs to that function. For example, for this function, it's the set of all numbers. And the codomain of a function is the set of all possible outputs of that function, which in this case is also numbers. Now, has anyone heard of total or partial functions? Awesome. I'm not talking about partially applied functions. That's a different concept. So functions can be pure or impure, and that is independent of whether they are total or partial. It's a pretty nice diagram, yes, thank you. A partial function is a function that is not defined for all possible inputs. So I want you to think about functions that don't always return a value or return undefined. Or it could even throw like an exception, it could be an infinite loop, or it could even crash your entire computer. So let's look at that half function again. Like clearly this is a pure function, right? It doesn't have any side effects, and it will always give you the same output for the input that you give it. However, it is a partial function because there are some inputs that we could pass into it that would cause it to throw an error. So let's look at all the possible domains and codomains for this function. We know that if we pass it a number, we'll get a number back. But if we pass it a string, it could either return a number or not a number. This is actually a feature, not a bug. JavaScript was designed to work in the worst of environments, and it will try its hardest to make your code at least run, even if you write terrible code. And you also have your other types like void, which is null or undefined. You have objects and arrays, which are special objects. And these all return not a number, which, by the way, is actually a number. Thanks, JavaScript. Fetch user takes a username as a string. It hits some API, returns a promise. And this is actually a partial function as well because the fetch could fail. I'd like to introduce you to something to make this function total. The promise now resolves with the user wrapped in an either type. And now this function can only return a promise that resolves to this either type. And whether or not the fetch fails, it will always return this type. So the either type encodes the 2 possible outcomes. It represents, or it returns left, which represents a failure, or right, which represents success. So what we have here is actually a monad, but I promised you no jargon, so don't worry about what that means. The idea, though, is that regardless of what you get back as an output, you want to return something with a similar interface, so you don't have to care if it was successful or a failure. Here's an example implementation or proof of this type signature. First, I'm going to fetch a user from my fake API, and then I'll return a left representing failure if the fetch is not 200 OK. And I'm also going to pass this function an error object, which I can use later, and note that the error is not thrown. If the fetch was successful, it returns a write, in this case, an object that matches my user interface. Now, when I use this function, note that whether or not it fails, the return value has a message that you can call safely. And this code that I have here won't cause any issues even if the fetch fails. When you get really into functional programming, you learn how to compose these concepts to do more cool things. So look up category theory later, or come speak to me and I'll blabber on about it. The cool thing about the either type is that you can capture the failure, and you can do something with it. So maybe here I could alert my user with an alert message or a toast message telling them that something went wrong. Let's look at one more example. This function detects the first element in the viewport inside of a scrollable container. Because this function can return undefined, it's a partial function as well. For example, what if I pass in a selector that yields no elements? We can reduce the codomain of this function to make this total by wrapping this in an option type. Now, every input to this function will give us an output in this codomain, which will never be undefined. The either type and the option type are quite similar. The main difference is that either also captures the failure value, while the option type does not. So the option really represents some value or nothing. This is the actual function implementation. And you can see that there are two places where it can be undefined. Document query selector will give you undefined if it doesn't find anything for that selector. And array.find will also return undefined if it doesn't find anything. So unlike the either type, you'll notice that we don't capture the reason for the failure. We just return the value none. And if we do find the first visible element, we'll return that. So now again, when I use this function, we'll get back an option type, which exposes a consistent interface, regardless of whether it was something or nothing. Both of these objects, some and none, have the map function defined, so my code won't throw an error like undefined is not a function. Finally, here's an example of a React component that fetches data. Because stateless functional components are pure functions, you can also make them total. This component lets me define 4 possible states: no data, the fetch is pending, the fetch has failed, and a successful case with data. Writing total functions mean that you think about fault tolerance up front. I mentioned earlier that domains and codomains of functions describe the set of all inputs and outputs. So we're really talking about set theory here, and cardinality in this context means the number of elements of the set. And I made a really bold claim earlier that the more specific your types and the more constraints you have in your code, the less likely you'll have bugs. This is not a silver bullet by any means, but lower cardinality means constraining the number of possible inputs into the function domain in order to make your code easier to reason about and to use. So let's start with the basics. A set is informally a collection of objects, and in our context, we want to think about the set of all values of the types that we're dealing with. So here I have a type called conferences, and note that this type is not a string, which would match every possible string. Because there are only 3 possible values for this type, we say that the cardinality of the conferences type is 3. But if conferences was just a string type, then there could be an infinite amount of strings that would match this type. So what I mean by this is that primitive types are often not precise. So let's look at the cardinality of all the primitive types we have in JavaScript. The only types with finite cardinality are Boolean, null, and undefined. And unless you like pain, you probably don't want to write a program just using those types. And even the non-primitive type object has an infinite cardinality because any possible object that you can define would match this type. So defining precise types can really help you reduce the number of bugs in your code. So let's look at some examples. Here I have a generic function toString, which calls the toString method on the object that's passed into it. And even though null and undefined don't have toString defined, for some reason this still type checks. And what this means is that you have lost type safety because it will cause a type error if you run this code. So this is what we call an unbounded generic function, which means that t, the type variable, can be literally any type. And we always want to stay away from the any type because it's not precise. We know from our earlier shenanigans that null and undefined give us type errors. So we want to make this a bounded generic function. To do this, we add a constraint to our generic type. Non-nullable is not code, but it's a type that constrains our generic type t. It tells TypeScript to exclude nulls and undefineds from t. And now, assuming that everything else has toString defined on it, we have made this function total, and since it will always return for every possible input. To put this visually, imagine a Venn diagram with two sets. One is the set of nullable types, which are null and undefined, and one is the set of all the types. And here I only have listed the default JavaScript types, but the types that you define would be members of this set too. And what you really want here is the difference, right? You want all of the types minus the nullable types, which would leave us with only the non-nullable types. The non-nullable type is implemented with conditional types, which is a new feature in TypeScript 2.8. And it's the basis for many of the new helper types they've just added, which are really, really awesome. And it now ships with these helpers built into TypeScript now. And it's very useful when you're starting to think about adding constraints to your code. You can check them out in the TypeScript source. There's a link in the slide. Oh, I'm so thirsty. Copy pasting, yes. We've talked a lot about functions and functional programming concepts, but keep in mind that you should be pragmatic. JavaScript is a multi-paradigm language, so you can do both object-oriented and functional programming. But TypeScript is really pragmatic. It strikes, in my opinion, the right balance between productivity and type safety. And you don't have to go all in to benefit from it. And TypeScript won't solve all of your bugs, but you should be able to catch the obvious ones before your users do. And again, think about constraints, think about fault tolerance, and make your functions total where it makes sense. I want to close off by briefly talking about GraphQL. If you're not familiar, it's an alternative to REST and lets you build up a strongly typed schema that describes your entire object graph. GraphQL has a great user experience. For example, here we have Graphical, a visual playground that you can mount on top of any GraphQL API. And you can also explore the schema here, which lets you know all the type details for each field in your schema. The really nice thing about this is that you get a lot of the same developer ergonomics as you would in TypeScript, Flow, Reason, or any other type language. And the only difference here is that the type system is now communicating to you over the wire. And being able to drill down into the schema as you're developing is a really great developer experience. And again, because it has a type system, advanced tools such as these can be built on top of them. The GraphQL type system is still evolving, and there's so much potential in where it could go. So just imagine a future for a moment where you have a distributed type system with type safety, when you as a UI engineer work with your API or even multiple microservices. We've discussed a lot today. First, we looked at an introduction to basic types in TypeScript. We looked at generics and how to read type signatures. Then we looked to functional programming to see how it can help us write better functions that are both pure and total. We explored a high-level introduction to the Curry-Howard-Lambeck correspondence, the idea that propositions are types, programs are proofs of those propositions, and that type checking is really the same as proof checking. And lastly, we looked briefly at GraphQL, and we explored what type systems can give you, even when delivered over the network. And I can't wait to see what else is coming. We've only scratched the surface today, but I hope you learned something about type systems and functional programming. And by the way, quick plug, I'm also hiring, so if you want to work on full-stack TypeScript, come speak to me later or DM me on Twitter. I want to thank Jameson and the organizers for having me at my first ever React Rally, and also a big thank you to Amanda, the amazing stenographer, for making this conference accessible.